Hi everyone, this is the second in a series of 5 videos for the topic Linear Relationships for Year 10. So where are we at? We've looked at the midpoint formula and the gradient formula, and so in this video we're going to look at the distance formula. Now recall that Pythagoras' theorem is used to find the length of an unknown side in a right-angled triangle. And if we've got a triangle like this, we don't know the hypotenuse, then we're going to say x squared, or the square of the hypotenuse, is going to be equal to the sum of the squares of the two shorter sides. So x squared is equal to 6 squared plus 7 squared. And working this out, we're going to get 36 plus 49, which is 85. And so x is going to be equal to the square root of 85, which is approximately equal to 9.2 centimeters. Now in Year 9, we learned how to use Pythagoras' theorem to find the distance between 2 points on a Cartesian plane. And we did that by drawing up a right-angled triangle between the 2 points and then working out the rise and the run. And just using Pythagoras' theorem, we're going to call this length of this hypotenuse d for distance, and so d squared will be equal to 3 squared plus 4 squared. Now 3 squared plus 4 squared, of course, is 25, and so the distance between those 2 points is 5. Here's another one. Find the distance between the points 1, -2 and 3, -5. So I've plotted the points and drawn up the right-angled triangle. Now note, we could have drawn the right-angled triangle on this side and that would be perfectly fine. We need to know this distance here. We're just going to count it. 1, 2, 3. So it's 3 units. And along here is 2 units. And then this is d. So d squared is going to be equal to 3 squared plus 2 squared, which is equal to 13. And so d is going to be the square root of 13, which we can write in exact form, or we can approximate it, and it's 3.6. Now, just like we did with gradient and midpoint, we can continue to use Pythagoras' theorem to work out the distance, or we can derive a formula. We're just going to use the same method though, but we've taken some generic points. This is our x1, y1 point, and this is x2, y2. I've drawn up the right-angled triangle, and I've worked out the length of the rise, which is just going to be the difference in the y-coordinates, and I've worked out the length of the run, which is going to be the difference in the x-coordinates. Okay, we're going to do Pythagoras' theorem. So d squared will equal x2 minus x1 all squared plus y2 minus y1 all squared, and we just got to take the square root. Now you notice that we don't do plus or minus here. Remember when we solve a quadratic, we always have to take the plus or minus, and the reason is because distance can only ever be positive, so we don't need to worry about plus or minus in this case. And there's our distance formula. Here's an example. Find the distance between the points 0, 1 and 5, -11. So let's begin with the formula. And just like I did in the first video, I'm going to start by writing the x1, y1 above this point and x2, y2 above this point. You won't need to do this very long before you get the hang of it. Now remember, doesn't matter which point we label as point 1 and which one we label as point 2, as long as we're consistent. Alright, so x2 is 5, then we're going to take away 0 and then square it, plus. And then we're going to do -11, take away 1, and then square it. Okay, now be patient when you're working this out because of the negatives. This part's alright, this is 5 squared, which is 25, plus we've got -12 here, all squared. So remember, when we've got a negative inside a bracket and we're squaring it, that's going to become positive because this is negative times a negative. So this is 25 plus 144, which gives us 169, and the square root of 169 is 13. Let's do another one. Find the distance between the points 2, -5 and -2, 3. All right, let's see how we go. Here's x2, so this is -2 take away 2, all squared, plus y2 is here, 3 take away -5. Don't forget those two minus signs in here. That makes a plus, remember. So this is -4 all squared plus 8 squared. All right, -4 all squared is 16 plus 64, which gives us a square root of 80. Now, if we're asked to leave it in exact form, we would then reduce that down. 16 goes into 80. So I take that out, I've got 4√5. So that's in simplest surd form. If I'm asked to give an approximation, I put it in the calculator. it's approximately equal to 8.94. Okay, let's move on to a slightly more complicated question. Quadrilateral ABCD has vertices given by the points A, which is 0, 3, B, -3, -1, C, 1, -4, and D, 4, 0. Calculate the lengths of the diagonals AC and BD. All right, so we're going to use this point and this one here and work out the distance between the points. We'll start with the formula. So x2 is 1 and x1 is 0. So we're going to do 1 take away 0 all squared. And then we're going to do -4 take away 3 all squared. This is 1 squared, that's all right. And this is -7 all squared, which is 49. So that's the square root of 50. And we'll just reduce that down to 5√2. Now let's work out the length of the diagonal BD. Start with the formula. It's these 2 points here. So x2 is 4. So 4 take away -3 all squared plus 0 take away -1 all squared. Be careful with all of those negatives. These are all going to become pluses. So this is 7 squared, which is 49, and 1 squared. So that's going to give us a square root of 50, which is equal to 5√2. Based on this information, what type of quadrilateral could this be? So our diagonals are equal. So we can see that it's not going to be a rhombus because the diagonals through here and here are not equal. It can't be a parallelogram and it can't be a kite. It could be a rectangle, it could be a square, and it could be a trapezium, but only if the trapezium is an isosceles trapezium, which means that those two sides are equal. C. Determine whether this shape is a rectangle or a square. So we're being told that it's not an isosceles trapezium, which is great. But how do we tell the difference between a rectangle or a square? Because both of them have got diagonals that are equal to one another. We need to look at adjacent sides. Remember, adjacent means next to one another. So if we look at a pair of adjacent sides and we find that they're equal, then we've got a square. And if we don't, then we've got a rectangle. So let's work out the length of the side AB and then the length of the side BC. All right, so here's A and B. So we're going to do -3 take 0 all squared plus -1 take 3 all squared. So this is -3 all squared, which is 9, and this is -4 all squared, which is 16, which gives us a square root of 25, which is 5. Now let's work out the length of side BC. So we've got 1 take away -3 all squared and -4 take away -1 all squared. Tidying that up, I've got 1 plus 3 is 4 squared, which is 16, plus -4 plus 1, that's -3, all squared is 9, which is the square root of 25, which is equal to 5. And so because our adjacent sides are equal, then we've got a square. We don't have to test all 4 of them because as soon as 2 of them end up being equal, the others will follow. So in conclusion, since one pair of adjacent sides are equal, ABCD is a square. Okay, that brings us to the end of this lesson. In our next lesson, we're going to look at graphing linear relationships.